Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am very happy to have Sultan Hassan with us today. Hello, Sultan.
Hello, how are you doing?
I am doing awesome on this December 8th of 2023 as we record this. And Sultan, where are you located at?
I am now in New York University, New York City.
Is there snow on the ground in New York yet?
No, not yet, but it's really, it's very cold. It seems like a very cold winter this time.
Okay. Okay. And I'm in Phoenix, and we get a little chilly in the morning, nothing like New York, but we will warm up to a very comfortable 75 or so today in the afternoon. So be very nice. Cool. And Sultan, what do you like to do for research?
Yeah, so I started in my PhD to do reionization science. Reionization is very interesting field, right? Because if you care about the reionization into the large scales, you need to really care about where the photons coming from. So you need to care about interstellar medium and CGM. You need to follow the journey of the photons, right?
Yep.
And that's naturally connects you to many fields. So then you find yourself thinking about ISM stuff, thinking about CGM, thinking about IEM, and I do lots of machine learning too. So
Oh, very good, very good. And that is going to bring us to this very awesome APJ letter. It is open access. It's the open access era, people. Go grab a copy for free. Get one. JWST constraints on the UV luminosity density at cosmic dawn. Implications for 21 centimeter cosmology. And Sultan, take us away.
Yeah, so before I talk about this, I would like to tell a bit like a small story about how this is all came about, right?
Cool.
So as I said, I'm coming from reionization from the 21 centimeter field, and then we had a debate at that time, right? So we had a debate. We have the detection by the edges experiments, right, for the 21 centimeter signal. And then people didn't believe it because it was too deep, and people talk about, okay, so whenever you have a tension between your measurement and theory, right?
Yep.
There is three different ways to think about it, right? So you could either blame the cosmology and you say, oh, the problem is from the cosmology, or maybe the problem from the astrophysics, or maybe there is no problem in the astrophysics or the cosmology, but then the measurements is wrong.
Fair enough. Okay, there's three.
Right? So you can do this. So we had this debate about people trying to tweak the cosmology, tweak the astrophysics, and that's it. So that was a debate 2018. Yep. Now we had the successful launch in JWST, and JWST, of course, started to probe the high redshift universe.
Yes.
And we started to have the similar debate.
Okay.
Right? So the similar debate is that, okay, so the detection of the bright sources in the early universe by JWST, models cannot really reproduce these. They have a very high density, like abundance of galaxies.
Yes.
So velocity function is very low. So then people started to have the same debate since January, right? It's a very lively debate, whether it's cosmology or whether it's astrophysics or whether maybe the measurement is wrong, redshift estimates, photometrics.
Yeah, whatever, right.
Right? So there are so many debates. Then I started to witness this, and like I watched this, and then I realized, wow, this is exactly the same debate we had before. Now the question is, right, what was very interesting to me is that both communities in the galaxy formation community by JWST or the 21 centimeter radio cosmology, right, they use different arguments for cosmology. They use different things for uncertainties because the experiment is different. But what was very interesting is that to see they use the same astrophysics story.
Sure.
Both of them, they require to have very too efficient star formation in the early universe.
Okay.
So then you can naturally get this deep signal, or you can actually recover models can reproduce the luminosity function estimates by JWST in the early universe. Yep. So then I started to think about it. I thought, you know what? There must be something here. There must be something here. This is the same debate, right?
Yes.
And the basic idea, how do you connect these two, right, is the fact that to have a 21 centimeter signal, right, to have that is happening to trigger that signal, you need enough Lyman alpha photons in the universe.
Yes.
Right? And
Yep.
that, and as the edges said, like redshift to 17 or 18 or whatever, at that time, we should have so many photons, Lyman alpha photons. And that's coming from the early galaxies that hopefully JWST detected. So that's, here is the connection, right? So then we can, this is the interesting part, and how you connect this experiment is that the question we are asking here is that whether the earliest population of galaxies that JWST detected would really provide enough photons to cause a 21 centimeter signal.
Yes, I'm with you.
That's the catch. Okay, so then we had the KITB workshop in Santa Barbara, and in the KITB workshop, it was for data-driven astronomy, and we had all these wonderful authors there. Most of them, they were there. And then we started to chat about this, and then we had like a blackboard about it, and then our actually discussion and everything with these amazing authors is really came about in that interaction in person in KITB. We with Chris and with Mark and Madao. I met actually Madao in a different university. So I was visiting a university which was like NYU Abu Dhabi, and I realized he was there doing his sabbatical. So we talked with him as well, and we had a very lively discussion with all these amazing authors. Yeah, so then we started to talk about this, and then after the KITB, we started to draft it, and it's been really fun to see how this is being shaped, and I think it like I think, to me, what I feel about is that this is really a very, very important work. It will open up many stories, so we can go ahead and skim through the paper.
Very cool. And for those who don't know, KITP is the Kavli Institute for Theoretical Physics at UC Santa Barbara.
Right. Yeah.
There we go.
Yeah, okay. So we talked about the whole introduction, right? Like, what is the JWST, right? And then and then how this is here, mostly how it's connected. So then what is one of the very interesting, so the question we're highlighting here, so if you can go down to the question, maybe up, it's probably here. So can young galaxies, so in the last paragraph before section 2, right? So this is the question we want to answer, right? If you can highlight that, can the young galaxies detected by JWST at the highest redshift provide enough Lyman alpha photons, right? To mix, right? Because the 21 centimeter in the beginning is only coupled to the CMB, right?
Yes.
So to decouple that from the CMB, and then you couple the spin temperature to the kinetic energy of the gas, you need enough Lyman alpha photons.
Indeed. Yep.
So that's where JWST come in. So the question is that, okay, we have these bright sources detected by JWST. Can we really say they have enough photons to produce that, right? So one of the things here is that this work was mainly inspired by the earlier attempt by Madao in 2018, where he was looking at, which we will come to it now when we talk about figure 1, but I want to stress the fact that he made the first study where he tried to connect to see what one of the things that you can do, basically, you can take the 21 centimeter profile, right, which we will see in a minute.
Back out.
Then you can convert it back and ask the question, what would be the UV density required in order to have that profile? So he made that calculation, and then he looked into how the evolution, which we will see in the minute. And here is just, we wanted to refine this analysis by including JWST. And then we looked at something else, which is also the presence of the excess in the radio background. Okay, so maybe let's just go to figure 1, and that makes it much easier to explain the whole story. So maybe we zoom in the left panel.
Let's zoom in on the left, and just for people know, these symbols we will get explained. Okay, on the left.
Right. So so this is what we see here. This is the total density, the total UV density, right? As a function of redshift. So this is basically, you have all the sources, you count all the UV, you add them up, you divide by the density, you're done. You have this This is the total.
So
Very simple, and it's very interesting. It captures many information, right?
Yeah.
And it's also probably the least biased quantities in the measurements, besides redshifts and other things, because it's very you don't have any, like, if you want to estimate masses, you need to assume some things.
Yes.
But this is just accounting, right, and stuff. So we have this, right? So what we see here, let's focus on the left here by redshift from 4 and 8.
Okay.
All these faint symbol, yeah, like we have this hexagon and whatever, all these faint symbols, this is coming from HST estimates.
Okay.
By Bowen et al. And many authors. So we have here so these authors, they have this any faint symbol here. This is coming from HST.
Yes.
Right.
Yes.
Any bright symbols here is JWST. So anything with the error bar is the JWST, and the error bar basically quantifies like the uncertainty in the faint end of the luminosity function, because we don't know. I mean, we didn't detect many of the faint galaxies in the early universe, and many of the luminosity functions here, they are really measured by only one galaxy, and they tell you, oh, this is the luminosity function. So there is some bias there. So that's why we add this. So how do you calculate this quantity? The way you do it is that we take the measured luminosity function. So we believe any measurement. So we are not saying that we take the measurement as it is, right? Although we know many of these luminosity function, maybe they have been estimated using one galaxy or two galaxies, but that's okay. It's high redshift. It's very hard. It's good to have at least upper limits or something. So we take the measured luminosity function.
Okay.
Then to calculate this quantity, you need to integrate down to some magnitude limit.
Yes.
So the magnitude limit here is minus 18, because it's basically, as it's written up in the title here, it's minus 18 because this this is where like maybe the sensitivity of HST, or maybe this is the like commonly adopted limit in the observation by HST. So let's go to minus 18. You take the measured luminosity function, you integrate it down to this limit,
Yep.
and then you sum up, right? And then you divide, you get that. Done. That's very easy, right? Now here, what we wanted to see here is that, so the faint symbols is HST. These bright symbols like this magenta and green, right?
Yes.
All these coming from JWST.
Yes.
Right? Harkani and Donan, right? Et al. And right? And what about this square, right? So we have 3 different squares here.
Yes.
So, okay, these different squares coming from the fact, so let's look at the red one. So let's look at the red box, which is the small, the lowest one.
Yes.
So red box is basically, if you follow the calculation of, like, if you want to ask the question, how much rho UV I need to have 21 centimeter signal at that redshift? That's the question, right? So you go with the models of, if you assume like metal poor stars in the early universe and you calculate things, you come up with this number of the box here, the red box. So that's, we call it the minimal coupling. It's the minimum amount of photons required to decouple the spin temperature from the CMB so you can see a signal.
Yes.
Right? So that's the beginning of the signal. We don't talk. So the end of the signal has different physics. But like, in order to say, Edges said there is signal at redshift to 17. So how do we say that? So then you take that signal. Okay, we take only the fact that redshift to 17. And then we ask the question, what is the rho UV density required? Like the minimum amount required to have a signal. So if you calculate that, you find this is the red box.
Yes.
Right?
Yep.
Then we know at the early universe, it's not only the CMB. That takes us maybe to equation 1. So if you go to equation 1, if you can, in the early universe, we usually think there is additional sources of radio background. This is the TRAD.
TRAD, yes.
There is additional. So if you assume only the CMB, you get the red box we were talking about, right? If you assume additional radio background, excessive radio background, which could be black holes, it could be from another experiment called Arcade 2. It could be from any, you can invoke your favorite scenario. But if you add addition, because we don't know, right? If you add additional source of radiation, which there are many arguments for it to exist, then that will boost the minimum constraints up. Correct. So then that's why you go up. So if you assume And that gives you a boost factor. So the boost factor is basically coming from the equation we have seen now, and then how much we should boost the minimum constraints if we have radiation background, and that will actually boost. If you assume only there is like black holes, that the source, supermassive black holes in the early universe, the source of the radio background, then they have a boost by a factor of 3, and that takes us to the brown box.
Got it.
And if you assume even a more strong radio background access, like what was measured in the arcade, which is astronomy. Could you go up to the next to the equation? We can see the full name because I can't remember the name of the experiments. But I think if you go left, right, yeah. So there it must be here arcade, which is the absolute radiometer for cosmology, astrophysics, and diffuse emission. Yes. So this experiment here, it has also measured some background, and they have some model. If you calculate that from the model, you realize you need a boost factor by 20. And this is the boost factor by 20 you find because they have a very strong emission. And that takes the red box
to the black.
To the black, yes. Right? Now let's look at this plot again. Okay, so we combined, this is here the magic, right? You can use rho UV to connect all these different experiments together, because now we all in equal footing in the same quantity of rho UV. We have HST experiments, which is the faint symbols. We have JWST in the bright symbols. We have the 3 black boxes from 21 centimeters.
Targets, okay.
Right? Now the question here, how do we answer the question? The question was, can JWST, right, provide enough photons to cause a 21 centimeter signal or not? So now if we look at this, and if you integrate down to -18, what we see as you go from redshift to 4, there is a gradual evolution in rho UV, right, up to redshift 12, right? And if you continue with that, maybe you will miss matching the boxes. So you cannot really, it's very hard to find a model that can connect the red, at least the red. The black is already very difficult.
The black's out of question.
Right? But how do you connect the red? So unless you have like something like goes gradually and then flattens, and that requires you to have some kind of formation or some suppression of a star formation in the early universe, which is very hard to, physically is very hard. So you need some kind of, like, people know that there is a gradual evolution. But the nice thing about this here is that at least JWST up to redshift of 12 is really kind of extrapolation to the HST results. So it's kind of going into the same direction, and it confirms what we have seen with HST, okay? So now we ask the question, right? What is really important in the early universe is the faint sources. So how about if we go to even a fainter end? And that takes us to the right panel.
All righty.
So if we integrate down to -13, the magic happens. You know, now if you look only at the red box, right, with HST and JWST, they all following a very gradual evolution of rho UV, which means that, right, and of course now the error bar in JWST will be bigger because now you are going to the faint end where we don't have really much constraints from JWST. So that's why you have this big error bars. But there is a gradual evolution. So you could say, well, yes, the sources that has been detected by JWST could really provide enough photons, because as you see here, like the red line could be a good fit for what is the minimum coupling constraints you expect from 21 centimeter signal. And all the measurements in the intermediate psi, like the intermediate redshifts, like 10, 12, something, they are still matching that, right?
They're still in the box,
Yeah, they're still in the box, and the uncertainty is large. So yeah, so hopefully with the more future observation, we can narrow this range, right? If we have more observation by redshift of 14, 15, right? Then we can really, maybe we can by 14 or whatever, we can narrow the area, and we know, right? Now, the other question is that, okay, so now we agree. According to this analysis, the minimum coupling is really consistent with the gradual extrapolation of the rho UV as it's coming from HST and JWST. Now the question is that, okay, can JWST now provide independent constraints on the radio background excess or not?
Fair.
Because we can
Fair.
ask the question now, right? So it's and
Yes.
that's interesting here is that is JWST. Now you look at the brown box and you do the align the brown line,
Yes.
and you realize because the error bar is big and everything, yes, it's still consistent, right? We can go even more to the extreme case where the black is only in the blank. And if you go to this black, because it boosts the constraint so much, you already at the same level of the rho UV by redshift 468.
Yeah.
So then that suggests that maybe a flat rho UV
Yes.
would really, like if you want to use the observation to place constraints on this, then you can say, well, maybe yes, maybe the black is also because we don't have much of measurements here to constrain this measurement from redshift of 12 to 16. But what is interesting here is that is that JWST not only would be able to tell us if there is 21 centimeter signal or not, but can also tell us about the radio background excess. And that's very interesting into the cosmos. So in other words, actually, you can use the JWST to make independent confirmation of 21 centimeter signal, and you can use the 21 centimeter signal to make independent confirmation to JWST sources. So this is a very interesting regime, and this is how you can. I mean, I think if we want to maximize the retrieval of information from observation, we really need to be looking now at connecting experiments, because now we are really JWST is going high, like up to early universe. And the 21 centimeter experiment pushing the limit to low redshift universe. So we have to meet, we have to talk, we have to find the way. And this is, we find it very interesting, is that you can really use the constraints. Of course, the having a very flat evolution in the rho UV may be physically unlikely, because we know there should be like some growth of sources gradually, right? But we don't know. So it would be nice, like when we have the measurements in the future here, like at redshift of 14 or 15, we would be starting to place them, and then we hopefully would be able to discriminate between these scenarios, whether it's.
You want to say a few words about the purple stars here or the purple points from Bowen? I mean, you get the impression there's this upturn.
Right. And so this upturn coming because also of the because of the cosmic variance estimates, right? So they don't have lots of sources in the higher redshift, and that's why they overestimate. But these are just used as an upper limit. So I wanted to put them, actually. I was thinking maybe remove them, put them, but I think I wanted to put them because I wanted to show that there is measurements here, and we want to see the uncertainties in the measurements, and tells us, like, because nobody would, like, when you see them you wouldn't believe them. Why would it really go up, right? So
I'm glad you left them. Thank you. Good. Okay.
Okay, so this is the good thing. So now we agree you can really do the minimal coupling, you can make dependent constraints on the radio background excess. Now the question interesting here is that, right? Now we kind of used JWST to say something about 21 centimeter. Now the question, can we use something about 21 centimeter to give something back to JWST? And that takes us to the second figure, which is basically here. It's coming from this table. So let's look at the table.
Yeah, let's look at the table. I was going to say.
Right. So in the table, what you can do is that, so what you see here, like the minimal coupling, the radio excess by black hole or arcade 2, what you see here in the second column, these are the rho UV estimate. This is basically the same estimate when we draw these black boxes. So the black box, the red box, the brown box. These are the constraints, right? So what we can do, we can assume a Schechter form for the luminosity function, right?
Okay. Yes.
Then we integrate that, right, to the certain cutoff, like 10 to like minus 13. And then we use fixed parameters. So the Schechter form has 3 parameters. You have the characteristic magnitude, you have the amplitude, and you have the what is it called? The alpha, which is the slope, right? So you have So we follow the observation at redshift of 16 and 15 and 14. And then we use the same the same procedure, which is we fix alpha to a value, which is taken from the observation, and then we fix, which is the value here, it's -235,
Yep.
and then we fix the characteristic magnitude to -19,
Okay.
and we only vary the amplitude. Of course, this is not an extensive MCMC fitting to vary all the parameters.
Yeah. Okay.
Stuff, but at least it can give us sense, and also because this is just what the observation they do. They never really they only vary the amplitude. So we followed the same method. And then if you just assume this Schechter form, you integrate down, and then you try to fit, you try to fit,
Okay.
then you get the amplitudes. What are the amplitudes required to match the same rho UV?
Yes.
And then you take these best fitting functions, which is can now fit best fit parameters of the luminosity function, and then you can draw your rho UV. And now you can have actually prediction for the luminosity function coming from 21 centimeter.
Cool.
Because now we are using the rho UV coming from 21 centimeter to predict what the luminosity function.
Right.
And that will take us to figure 2, where we show this is the luminosity function at redshift of 16, right? And as again, you have the red one is coming from the minimal coupling. Of course, the radio background will boost things. That's why you have a boost in the brown and the black.
Yep.
Then we compare that with the measurements. So we have the measurements by Hurricane, the blue one at redshift of 16, but that's extrapolated because that was from the luminosity function parameters for some fits that were provided for the low redshift at redshift of 12, 11. So if you take these fits and you extrapolate them to 16, you can come up with the blue. So comparing with that, with the blue, our luminosity functions, they are much higher than the extrapolation, right? Which suggests that we should really see much more sources if we expect to have a signal at these redshifts.
Okay.
Then you can compare with the upper limit, the measured upper limit, which is the blue error bar. And all the luminosity function at that limit, they are much lower than this. So we are okay. So we are still down to the upper limit. It's okay. Now look at redshift 2. Now let's compare with redshift of 12, because what we expect is that the luminosity function should go from low, right? The amplitude should be low, and then gradually go up as you go to low redshift. So at 12 here, this is the dashed line, and it's also estimates coming from some lower limits. That's why you see the arrows, error bars going up. So now if you compare with this, you realize, well, maybe the minimal coupling is lower than that. That's okay. That's a random evaluation, right? But then the brown is the faint end, which is also not constrained. We are fixing that. But this prediction looks like much higher than 12. So maybe that doesn't make sense. But at the same time, if you look at the 12, you realize there is its lower limit. So that might go up. So we don't know, right? And at the same, you could be said by the black line, because the black line is higher than 12, which doesn't make sense. But we have error bar going up, so we don't know. Maybe it goes up. So it's just an exercise to say that, okay, if you expect a 21 centimeter, a redshift of 16, and you just for minimal coupling or from any radiation excess, you can predict the form of the luminosity function. And then we can, and this is what we require. This is the number of galaxies required at different magnitudes to cause the 21 centimeter at that redshift. And now, hopefully, with the future observation, we can really tell what happens here. Then the question here, the last question we talk about in this paper is that whether really, can you really see signal before? Could JWST tell you if you can even see a 21 centimeter signal before redshift of 17? Claim, or lower than that? And what would we need it to prevent that? So that takes us to the last figure, which is the figure for the 21 centimeter profile.
Which was the initial question. So
this is here the profile, the brightness temperature profile at a function of redshift in the top axis, bottom axis is the frequency, right? So we coming from left to right, early universe going to low redshift universe. So the yellow is the signal, the measured signal by edges, which is people think it's very deep and all that, and it has this
Yes.
debate
A
in the
lot of
theory.
discussion on that. Yep.
Right. So if we take the raw UV fit that we have, that red line, and we basically go back in the calculation, put it as an input to find out what would be the 21 centimeter signal would be, what would be the brightness temperature would be if we take the fit and propagate it back into the calculation.
Yes.
We get the red solid line.
Yes.
And that red solid line, what would tell you is that you could really see a signal before that, because the signal is not zero, right? The signal is not zero. So it's not zero. But if you want the signal to start at the same time as the edges, then you have to have a cutoff
Yep.
in the raw UV to start. So which means that like the population and the earliest galaxies, they should come around redshift of 20, 21, something like that. And then before that, everything is zero. There is nothing really. You don't have any signal.
Right.
So by that, you can really match that. And here really takes you to very interesting questions. Of course, the signal is not as deep as this as measured signal. And maybe also the question is that whether really, okay, so would this signal be detected? Maybe this signal is very shallow, is not really that deep. So maybe it's also hard to observe. So we hope also, so all the thing here we take from this is that there is a signal around redshift of 17 or 18, as claimed by the edges. And we hope in the future we would, so what we see here is that it could be anywhere now, depending on what is the magnitude, what is the raw UV cutoff you use, what is the form of the raw UV required. But if you use this minimal coupling and you cut everything wherever, you can get the signal starting from redshift of 20, 21. But then in order to get this signal to go back up, you need X-ray hating, and we don't have X-ray hating in our model. So in our calculation, we wanted to see the beginning of the signal. That's a difference astrophysics, because we wanted to see like what, like how, whether JWST really observation can tell us anything about this signal.
Gotcha.
And yeah, and we're quite happy with that. Is that I think that just concludes the main paper. Is that I think we demonstrated in the paper a very powerful technique to connect different experiments.
Indeed. Yes.
And we demonstrated that it's very important you can actually drive constraints on the presence of 21 centimeter signal from JWST and from like infrared and UV observation. And at the same time, you can actually use 21 centimeter to provide some prediction for JWST, right? So I think, and then we demonstrate that like what is the implication for the detection of the signal. And we see that you need really a cutoff around redshift of 21 to recover the edges, but the signal is not as deep, so which might be also very challenging to detect. So that would conclude everything. So we connected the experiments. We wanted actually to have the experiment speak to us. If we want to maximize and to extract the maximum amount of information, the only way to do it to have different experiments talk to each other.
Yep. Very cool. Very cool. Beautiful work. Beautiful work.
Yeah. I like it because it's very simple, and it doesn't require like running simulation for a long time and taking observation for a long time. It's a calculation you can do very quickly. Yeah.
You have to observe for a little bit. It's not.
Yeah. No, you can. Yeah, of course, observation is important and simulation is important. I do the simulation a lot. But what I'm saying is that this is like it's a very simplified calculation, clean. You can take measurement, luminosities, you integrate. It's not really complicated, and it turns out to have a very interesting connection between different experiments and fields.
Bands. Yeah, very cool. Very cool. Sultan, thank you so much for walking us through your very lovely letter.
Thank you for the time.
And you touched on it a little bit as you were going through, and so let me just push on it a little bit. Where do you think we go from here, or let's say over the next couple of years? Are there probably already JWST proposals to go back to even further redshift? Is there, you mentioned infrared, is there stuff we can do in the infrared? Is there other instruments? And so on, and just sort of next steps on where do we go with this topic in the near future?
Yeah, so I think I'm really like eagerly waiting for the upcoming surveys by JWST, because definitely they will probably provide more sources at redshift of 14 and 15 and 16, and that will tell us many things. It will help us to narrow down the range. It can tell us what would be the expected level for the background excess. When should we expect a signal, like for the radio experiments, is also useful to know this, because maybe we can focus more in these frequency ranges than other ranges, right? And that's really important. There are experiments coming, like SARAS, and probably the edges will come again about this. So there are many efforts to measure the 21 centimeter signal. And once we have that measurement, we now have a way to go back and predict things for JWST and HST. So I think it's a very interesting time. It's probably poorly understood, and we don't have lots of I think it also pushes the limit. I started now to think about modeling population 3 stars. What would be the physics, whatever, what are the nature for, I think that also tell us about what is the nature for sources detected by JWST. We don't know what are the nature of the sources in the early universe. We don't know this. It's very important to answer these questions.
Yes.
And I think we don't really know yet whether it's experiment. It's what is interesting is that we don't know it's uncertainties or it's astrophysics. We still have the problem, right? So you still can invoke your favorite scenario of dark matter and add a baryonic matter interaction or whatever, and then you change the number of halos and stuff. You can still have heavy initial mass function, heavy top initial mass function, and that will change the number of sources you would expect for JWST. Or maybe you have too efficient star formation, or maybe the feedback is too weak, or maybe too strong. They are, so it's very, I also started recently to think about maybe we can actually include the primordial fluctuations. So we have some constraints from the primordial fluctuations from the CMB, right? So that also might go into this story. Maybe we can actually, JWST maybe could actually put some constraints on the primordial fluctuations, right? And that's something I'm thinking about now, and hopefully I can do the same, which is actually what I would like to do, is to add fluctuations and then see how that changes the halo mass function. Then you can calculate the rho UV, then you have JWST, and then you go back, and then you try to make fittings and stuff, and it could be a really fun project to do. But it's on my list to do for sure. Very interesting.
I hope it's high up on your list.
So now we connect CMB and 21 centimeter and JWST, So now that's really cool. Yeah.
Very nice. Awesome. I really look forward to seeing this field develop over the next couple of years. It'll be very exciting. Very nice. Sultan, thank you so much again for walking us through your very lovely APJ letter. Thanks.
Thank you very much for the time. Thank you. Bye.
And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.